Good evening, ma'am.
Good evening, sir.
Ma'am, make me a host. Yeah, ma'am.
I made you, sir. Please
Yes,
continue.
Yesterday, we were learning about the properties of colloids. We know what is a colloid. It is a heterogeneous mixture. Heterogeneous mixture containing dispersed phase and dispersed medium. We know what is dispersed phase and dispersed medium. Based on that, we have learned the classification of colloids, 8 types of colloidal system. We are learning the physical properties of colloidal system. Any colloidal system, for that matter, it's a heterogeneous mixture. Now, it consists of 2 phases, dispersed phase and dispersed medium. It is highly stable. Any colloid, for that matter, is highly stable. Our colloidal solutions are quite very stable. Michael Faraday prepared a first colloidal solution of gold, which is even today it is stable. The first colloids were prepared by Michael Faraday. Filterability. Colloidal particles are readily passed through ordinary filter paper. Because ordinary filter paper, the pore size will be more. It's in micrometers. Colloids are in nanometers. Therefore, colloids can easily pass through ordinary filter paper. But it can be retained by special filters known as ultrafilters, or it's otherwise called as parchment paper bag. Now, this is physical properties. One is the nature, heterogeneous, stability, and filterability. The next property is colligative property. Due to the formation of associated molecules, these colloids will get associated. So observed value of the colligative properties like relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure are smaller than expected. So the molecular mass determined experimentally will be smaller than or lesser than the theoretical molecular mass. That is what it means. For a given colloidal salt, the number of particles will be very small as compared to the true solution. True solution is otherwise called as crystalloid. We learned till here in the last class. Now we have to learn with mechanical properties. We have 2 mechanical properties to be learned. That's not 2, 1, that is called as Brownian moment. Brownian moment, and next we have kinetic property, and also we have electrical property. We will learn kinetic property and electrical property a little later today. Now, the Brownian moment, this is an important question for your 12th standard. Not only this, mechanical properties, under that Brownian moment, we have optical property as well as we have electrical property, all are important. Now, Robert Brown, this Brownian moment is named on a botanist, Robert Brown. A botanist discovered in 1827 that pollen grains, when suspended in water, do not remain at rest, but move about continuously and randomly in all directions. So what happens? These pollen grains collide with water molecules and they move in randomly in all directions, and they keep on continuously moving. They are not stationary. They are mobile. Later on, it was observed that colloidal particles are also moving in random or in zigzag motion, and this type of motion is called as Brownian moment. So if you take a gold sol, what is a gold sol? Gold sol is gold particles in water. These gold particles are not stationary. So these gold particles are in random motion, disordered motion. Why they are in random motion is because they can collide with each other and they can change direction. or these particles can collide with the solvent particle, water molecules, and they can change the direction. Therefore, there is no orderly movement of this gold particles in gold salt. That disordered movement is termed as Brownian movement. This can be observed by using an ultra microscope. This can be observed using an ultra microscope. This ultra microscope is a microscope which has high resolving power. It can see the very small particles. Therefore, it's called ultra microscope. This ultra microscope was discovered by Zsigmondy, Zsigmondy. So ultra microscope was discovered by Zsigmondy. What is Brownian movement now? How do we define Brownian movement now? The movement, the zigzag movement, the random movement, or the haphazard movement, or the disorderly movement of colloidal particles due to the collision of colloidal particles with each other or with the dispersed medium is called as Brownian movement. So Brownian movement is the zigzag motion, random or zigzag motion of movement of colloidal particles due to the collision with each other, or with the medium, dispersed medium. Dispersed medium is called as Brownian movement. Brownian movement explains the force of gravity acting on colloidal particles. This helps in providing stability of the colloidal salts by not allowing to settle down. So due to the movement of these colloidal particles, or Brownian movement, the colloidal salts are highly stable. They do not settle at the bottom. So this diffusion concept, sedimentation concept, we do not have in our syllabus, so we will not talk about it in detail. But you should know what is Brownian movement. It is random movement or zigzag movement or disorderly movement of colloidal particles in a salt due is called as Brownian movement. Next, optical properties. The optical properties are, it is called as Tyndall effect. Optical properties are Tyndall effect. Now, optics stands for light. Optical properties are Tyndall effect. What is this optical property or Tyndall effect? Now, we have a source. Ma'am, kindly make me a host, ma'am. Something happened with my network. Ma'am? Ma'am?
Yes, sir.
And please make me a host, ma'am. Yes, something happened wrong.
I made you host, sir.
Yes, ma'am. Just give me some time, ma'am.
Sir, are you there?
Yeah, ma'am. Ma'am, just give me 1 minute time.
Yes.
Yes. Ma'am, can you see the screen?
No, sir.
Yeah, 1 minute, ma'am. Something wrong with this phone mic. 1 minute.
Yes, sir. Now it's
Yeah. Okay. Now, Tyndall effect. Tyndall effect is based on light. It's an optical effect. It is based on light. Optic stands for light. This is an optical property of a colloid. Now, source, when white light is passed through a true solution is a solution or a true solution also can be called as crystalloids, where the particle size is less than 1 nanometer. So what happens is the path in which the light travels will not be seen. So when you take a white source or a light, when it is passed through solution, the path in which the light travels cannot be seen. But the same white light, when you pass through a colloidal solution, Now what happens is the path in which light is traveling, the path in which light travels can be visible, can be seen. It is in the form of a cone. The path in which light travels can be seen. This is observed by using a microscope, ultra microscope. It's not seen through a naked eye. It is seen through an ultra microscope. Now, this scattering of light due to the colloidal particles is called as Tyndall effect. So what's Tyndall effect? They can ask you for 2 marks. Scattering of light due to colloidal particles is called as Tyndall effect. The path in which light travels, appears as a cone. Appears as a cone. Called as Tyndall cone. Called as Tyndall cone. So this effect is called as optical property, or this effect is called as Tyndall effect. Now, in the night times, when we start our vehicle and turn on the light of the vehicle, you can see the path in which light travels. Or early in the morning, on a sunny day, early in the morning, when you open the window, you can see the sunlight coming into the room. Along with that, you can see dust particles. So these when the light falls on the dust particles, what happens is the light gets scattered. Therefore, this effect is called as a Tyndall effect. Nothing but scattering of light due to the colloidal particles. The path in which the light travels appears as a cone called as Tyndall cone. You can see this is a Tyndall cone. This is called as Tyndall cone. The same light is passed through a true solution, but the path in which light travels is not visible through the microscope. But the same light, when you pass through a colloidal solution, and if you observe it through a microscope, the path in which light travels appears in the form of a cone called as Tyndall cone. Because here the particle size is between 1 nanometer to 100 nanometer. Since we have 1 nanometer to 100 nanometer, what happens is the light gets scattered. When light gets scattered, what happens? That appears to be in the form of a cone called as Tyndall cone. Now, Tyndall effect has also been observed by an instrument called as ultramicroscope. I told you Tyndall effect is observed by Tyndall effect. Now, some examples for the Tyndall effect are shown. Tail of a comet is seen in the form of a Tyndall cone due to the scattering of light. Tail of a comet, you know that. Due to the scattering, the sky looks blue. Sky is not having any color, but due to the scattering of the light, the sky looks blue in color. Blue in color. Visibility of a projector path and circus lights, they are also called, it's an example for Tyndall effect. In olden days, when we watched the movie in a theater, when you observe when you lift up your head and see the light traveling from the projector in the theater also can be seen, and you can see dust particle. That is also an example for Tyndall effect. Visibility of sharp ray of sunlight passing through a slit in the dark room is also called as Tyndall effect. So many examples are there for Tyndall effect. So Tyndall effect is defined as scattering of light due to the colloidal particles, and the path in which the light travels appears as a Tyndall cone. Appears as the Tyndall cone. Appears as a Tyndall cone. Now, the next property is electrical property. Now, this electrical property clearly says it is based on the current. Now, in electrical property, we have to learn something called as electrophoresis. Now, what is this electrophoresis? Now, you would take a glass tube, which is in the shape U. So, glass U tube like this. Into this, immerse two platinum electrodes. Immerse two platinum electrodes connected to the power supply. Connected to the power supply. Now, in order to find the charge, now for an example, if you take gold sol, this gold sol is an example for negative colloid. Now, this is anode and this is cathode. Now, gold sol is taken here. Gold sol. Now, this gold sol is taken, and to find the charge of the gold sol, I told you it is negative because by experiment we have found out that it's negatively charged. If you don't know what is the charge on the gold sol, you take it in a U tube, which is connected to the power supply, anode and cathode, platinum. Now, when you pass current, all the gold sol will move towards the positive electrode. Since the gold sol moved towards the positive electrode, we understand the charge on the gold sol is negative. Similarly, if you take ferric hydroxide sol, Now, this ferric hydroxide salt, when you pass current, this ferric hydroxide salt will move towards cathode. Since these ferric hydroxide salts moving towards cathode, cathode is a negative electrode. Positively charged particles only will move towards cathode. Therefore, this ferric hydroxide will be having positive charge. So, colloids are charged in nature. So, to determine the charge on the nature, in the charge of the colloid, we perform an experiment called electrophoresis. So the phenomenon of movement of colloidal particles under the applied electric field is called as electrophoresis. If the colloid moves towards anode, it is called as anaphoresis. And if the colloid moves at cathode, it is called as cataphoresis. Cataphoresis. So both anaphoresis and cataphoresis are commonly called as electrophoresis. If the particle accumulate near the negative electrode, the charge on the particle is positive. On the other hand, if the salt accumulate near the positive electrode, the charge on the particles, colloidal particles, are negative. This apparatus consists of U-tube with 2 platinum in each limb. This I clearly explained. This is called as electrophoresis. So in your 12th standard, they can ask you, what is anaphoresis? What is cataphoresis? Or what is electrophoresis? There can be a common question. So 3 properties of the colloids we have learned. One is the kinetic property. Brownian moment is a kinetic property. It is because of the movement of the colloidal particles. Next, we learned optical property. Tyndall effect is an example for optical property. Scatter of light due to the colloidal particles is called as Tyndall effect. The third electrical property we learned, this electrical property is called as electrophoresis, anaphoresis, and cataphoresis. The reverse of electrophoresis is called as sedimentation potential, or it is called as Dawn effect. The sedimentation potential is a setup when a particle is forced to move in a resting liquid. This phenomenon was discovered by Dawn, and it's called as Dawn effect. So reverse of electrophoresis. This is not in your syllabus for POC, but they can ask you for the competitive exams. What is the reverse of electrophoresis? The reverse of electrophoresis is called as Dawn effect. Now, electrical properties of the colloid are also can be explained by electrical double layer theory. According to this theory, a double layer of ion appear at the surface of the solid. Surface of the solid. Now, the electrical double layer we do not have in the syllabus. Now, electroosmosis is also not there in the syllabus, but in the movement of dispersed particle are prevented by moving by a semi-permeable membrane. We do not have this in the syllabus. Now, we have to learn the origin of charges. Why colloidal particles get charged? We have to understand this. So, the origin of charges is due to 2 reasons. One is dissociation of the surface molecules. We learned Michel formation. Now, above a particular concentration and above a particular temperature called as critical temperature, Kraft temperature and concentration, critical Michel concentration, soap will form Michels. So a soap will contain 2 parts. So this is sodium palmitate. Sodium palmitate. Now it contains 2 parts. One is called as hydrophilic. Hydrophilic. The other one is hydrophobic. Hydrophobic means the part of the molecule which is not having any affinity towards water will be called as hydrophobic. Now, this is hydrophobic in nature. This is hydrophobic in nature. Now, this hydrophobic part gets accumulated like this to form a soap mishell. To form a soap mishell like this. We have learned. Since it is undergoing ionization on the surface, the colloid will have a charge. That's negative charge. So soap mishells are negatively charged because it has undergone ionization at the surface. At the surface. Got ionization at the surface. Now, the second reason for colloidal particles to form charge is due to selective adsorption of ions. It is due to selective adsorption of ions. Now, what do you mean by selective adsorption of ions? Now, if you take an arsenous sulfide, AS2S3, this arsenous sulfide will preferentially adsorb only sulfide ions. When we say it adsorbs only sulfide ions, so arsenous sulfide will have S2- ions on the surface. It preferentially, even though it has arsenic ions, it will absorb only sulfide ions. This is because of a principle called as Le-Chatelier's principle. We will learn about we have learned about Le-Chatelier's principle in the first PUC. Similarly, the second example, if I have to give, now if you take ferric hydroxide, this ferric hydroxide will preferentially adsorb only ferric ions. If we take this as ferric hydroxide molecule, sorry, Fe3, this ferric hydroxide molecule will adsorb only ferric ions. Only ferric ions. So therefore, this ferric hydroxide is positively charged and this arsenous sulfide is negatively charged. So the two reasons why the colloids are charged. One is preferential adsorption on the surface. One is preferential adsorption on the surface. The second one is ionization on the surface. Ionization on the surface. So these are the two reasons for colloids to be charged. Here they've given an example, silver iodide. The silver iodide is neutral, but it preferentially adsorbs iodide ion. Therefore, the silver iodide is also an example for. They can ask you for 2 marks why colloids are charged. One is preferential adsorption. One is, or maybe you can write one is ionization on the surface. Ionization on the surface. The second reason is preferential adsorption. We know what is adsorption concept. Since colloids are also adsorbs certain molecules, we are learning this colloidal chapter, colloids chapter also on the surface chemistry. It is also a surface phenomena. You can see in case of AgI, if you take excess Ag plus, you will get positively charged colloid. If you take excess I minus, you will get a negative charge colloid. I minus gets adsorption on the surface are the reason for charges on the colloid. Now, some of the example for a negatively charged colloids, metal dispersion, gold, salts, platinum salt, all are negatively charged colloid. Acid dye, eosine, pango, red, salts of starch, gums, gold, gelatin, all these are negatively charged. So positively charged colloid. Metal hydroxides are positively charged. Metal oxides are positively charged. Methylene blue is positively charged. Hemoglobin is a positively charged colloid because it contains Fe2 plus ion. Sulfur salt is also an example for positively charged colloids. Now, stability of salts we do not have in our syllabus. Coagulation, flocculation, or precipitation. Now, what is this coagulation, flocculation, or precipitation? This coagulation, flocculation, or precipitation all means the same. Now, colloids are small particles ranging 1 to 100 nanometers. Now, these colloid particles aggregate with each other, join with each other, aggregate with each other, grow bigger in size, and finally it precipitates. So this process is called as coagulation, a process of precipitation of a colloidal solution by addition of excess of an electrolyte is called as coagulation, or it is called as flocculation, or it is called as precipitation. Now, what is this? Colloidal particles are very small in size. These colloidal particles can combine with each other to form a bigger particle, and the size keeps on going bigger, and finally they become a precipitate. That process is called as coagulation. So coagulation or flocculation, this is also very important for your exams. The phenomenon of precipitation of colloidal solutions by addition of an electrolyte, excess of an electrolyte, is called as coagulation. So coagulation of lyophobic salts can be carried out. The methods of coagulation we do not have in our syllabus, not to worry about it. Now, an important concept, important rule you should learn. Now, we will learn the rule little later. We will understand the concept now, and we will learn the rule later. Now, for an example, I have a negatively charged colloid. Negatively charged colloid. In order to coagulate negatively charged colloid, we need active ion. Now, when I say we need active ion, the active ion should be positive. So in order to coagulate negatively charged colloid, we need to have positive active ion. Now, similarly, if we have to coagulate positively charged colloid, we need negatively charged active ion. Now, when we say positively charged active ion here, in this case, to coagulate negatively charged colloid, I can write K plus, I can write Ca2 plus, or maybe I can write barium, not a Ca. Instead of Ca, we can take barium. We can write aluminum 3 plus. We can write titanium 4 plus. All these are active ions, but all these are positive ions. The active ion amongst this will be titanium. So the coagulating ability of titanium 4 plus will be greater than aluminum 3 plus, greater than barium 2 plus, greater than sodium plus or potassium, whatever, or monovalent. Now, Hardison Schultz rule we will define. Before that, again, we will learn. In order to coagulate positively charged colloid, we need negatively charged active ion. So when I say negatively charged active ion, Cl minus, SO4 2 minus, PO4 3 minus, FeCN6 4 minus. Now, order of this is FeCN6 ferrocyanide ion will have greater coagulating ability compared to phosphate ion, compared to sulfate ion, and sulfate will have greater coagulating capacity compared to chloride ion. Now, in case to coagulate the positively charged colloid, the active ion will be FeCN6 4 minus. Now, what is this? We'll understand it this way, in a simpler way, not a technical way, but it is a common way to understand what is Hardison Schultz rule. Now, if I'm talking about a negatively charged colloid, if we take K plus as an active ion, only one negatively charged colloid can form a bond with K+. But if I take one titanium 4+, 4 negatively charged colloid can get bonded to titanium. So that means the ability for the negative charged colloid to get precipitated with titanium is more compared to potassium. Or in other words, if I have to say, the amount of titanium ion required to coagulate the negatively charged colloid will be less compared to number of potassium ion required. Therefore, the coagulating ability of titanium is greater than all the other three. Similarly, in order to coagulate positively charged colloid, so FeCN6 4- is required in lesser quantity compared to all these. Therefore, this will be called as active ion. Now, what is this Hardy's and Schultz rule? Hardy's and Schultz rule states that greater the charge, greater is the coagulating ability. What is Hardy's and Schultz rule? Hardy's and Schultz rule states that greater charge, greater is the coagulating ability. Now, in case of coagulating the negatively charged colloid, titanium is the active ion. Titanium is greater. In order to coagulate positively charged colloid, FeCN6 4- is the active ion because the charge on Fe6 4- is more compared to all the other ions. This is called as Hardy's and Schultz rule. Now, what is this Hardy's and Schultz rule? The coagulating capacity of different electrolytes is different. It depends upon the valency of the active ion. Valency of the active ion, or we can learn it as charge on the active ion, and are called as flocculating ion. Coagulating ion is otherwise called as flocculating ion. According to Hardy's and Schultz rule, greater the valency of the active ion or the flocculating ion, greater will be its coagulating power, coagulating ability. All right. Hardy's and Schultz rule states ion carrying charge opposite to that of salt particles are effective in causing coagulation. I told you, in order to coagulate negative ion, we need to have positive active ion. In order to coagulate positively charged colloid, we need to have negative active ion. Now, coagulating power of an electrolyte is direct proportional to valency. So greater the charge, greater is the coagulating ability. So I've given you the examples. Arsenic sulfide is a negatively charged colloid. In order to coagulate the negatively charged colloid, we need to have positively charged active ion. So amongst these three, aluminum is more charged. So aluminum 3+ will be ability, coagulating power compared to other two. FeOH thrice is a positively charged colloid. So the negatively charged ion required is FeCN6. So the next is flocculation value or coagulation value. What is this flocculation value or coagulation value? The minimum concentration of an electrolyte. The minimum concentration of the electrolyte, which is required to cause the coagulation or flocculation of the sol, is known as flocculation value, or is otherwise known as coagulation value. Or we can define otherwise, the number of millimoles of electrolyte required to bring about coagulation of 1 liter of colloidal solution is called as flocculation value. What is flocculation value? They can ask you. Minimum concentration of an electrolyte, which is required to cause the coagulation or flocculation of a sol, is known as flocculation value. Or minimum number of millimoles of electrolyte required to bring about coagulation of 1 liter of colloidal solution is called as flocculation value. And the last part of the topic is gold number. This is important, gold number. What is this gold number? Now, gold number, the term introduced by a scientist named Zygmundi. Now, now, for an example, if you take a gold sol, water, and in this we have gold sol, gold particles like this. gold particles. Now, gold is heavier than water. We know that. If you leave it for some time, what happens? The gold particle will settle at the bottom. It forms a suspension. So we should prevent this to happen, not to happen. So gold particles should be distributed uniformly in water. So therefore, what we do is we add a protective colloid. Protective colloid. Generally, this protective colloid is lyophilic. Now, what do you mean by lyophilic? A colloid which has affinity towards the dispersed medium is called as lyophilic colloid. Is called as lyophilic colloid. Now, protecting power of different protective colloids is different. The efficiency of the protective colloid is expressed in terms of gold number. So this lyophilic colloids, which prevents the coagulation of a colloid, is not same for all. It is different for different protective colloid, lyophilic colloids. The efficiency of the protective colloid is expressed in terms of gold number. See, this is a gold colloid. In order to prevent this gold particles or gold colloid to undergo suspension, we add a protective colloid. That protective colloid is lyophilic in nature. This protective colloid, what we add, has different efficiency. Those efficiencies are expressed in terms. This gold number describes the protective power of different colloids. Gold number describes the protective power of different colloids. It is defined as the weight of the protective agent in milligrams. The weight of protective agent in milligrams, which when added to 100 ml of gold salt, it is just sufficient to prevent a color change from red to blue on addition of 1 ml of 10% sodium chloride solution is equal to the gold number. So it is defined as, now you can take a standard gold salt, standard gold salt, that is 0.0053 or 0.0058%. Now, to this standard gold salt, in order to prevent the suspension or coagulation of this gold salt, 10%, 1 ml of 10% sodium chloride is added. So that the color, it prevents the color change from red to blue. And this is called as gold number of protective colloid. So it's defined as number of a weight of a dried protective agent in milligrams, which when added to 10 ml of standard gold salt in order to, it's just sufficient to prevent the color change from red to blue on an addition of 1 ml of standard 10% sodium chloride solution is called as gold number. Smaller the gold number, higher is the protective action. This is important. Smaller the gold number, higher is the protective action. Our protective power is inversely proportional to gold number. Protective power is inversely proportional to gold number. So larger the value of the protective colloid, lesser will be the gold number. So that is what you should remember. So protective colloid is inversely proportional. Protective power is inversely proportional to gold number. Now, there are some examples for a protective colloid. These are the gold numbers. Now, gelatin 0.05 to 0.01, sodium caseinate 0.01, hemoglobin 0.03 to 0.07, gum arabic 0.15 to 0.25. So sodium oleate 0.4 to 1, and gum, this is potassium, potato starch, it's 25. So protective power is inversely proportional to gold number. So gold number of starch is high. So that means protective action of gold starch will be what? Less. Gelatin, gold number is less. So protective power of gelatin will be more. This is with respect to the chapter colloids. So we'll have to learn some of the questions. Emulsion and all we have learned. These are all we have learned in the regular colloids. What is gel? What is emulsion? All that we have learned. So we will not be talking about it again, we'll learn some of the questions. Or before we learn about the question, applications of colloids is important. We will learn the applications of colloids. So applications of colloids, the first one is purification of water by alum. It's called as coagulation. Purification of water by alum. Now, in the villages, even know, I don't know now, in the olden days, there used to be a tank at the corner of the road, and everybody used to go to the tank and get water for their need. So the tank will be generally opened. It's a large tank which will be generally opened. This will contain dust particles. So in order to prevent the dust particles, in order to remove the dust particle, what they use is they add potash alum. Potash alum. Dust is a colloid, negatively charged colloid. So in this potash alum, aluminium acts as an active ion. So what happens? All the dust particle will get accumulated, and finally there becomes a precipitate at the bottom and settle. Precipitate. So this water above water will be free from dust particle. So in clarification of water or purification of water, this is also determined as clarification, CLARI, clarification of water. So potash alum added aluminum 3+ ion is added to water to coagulate the negatively charged clay particle or dust particle. Next, in rubber and tanning industry, coagulation and several industry processes such as rubber plating, chrome tanning, dyeing, lubrication, etc. are of colloidal nature. And artificial rain. It is possible to cause artificial rain by throwing electrified sand or sodium iodide from aeroplane and thus coagulating the mist hanging in air. So silver iodide or electrified sand, if you spray or throw from the aeroplane, they coagulate the mist particles hanging from in the air and causes rain. Causes rain. The next application is smoke precipitation. The smoke precipitation is also consisting of carbon particles, dispersed in air. Thus, these particles are removed by passing through a chamber provided with high positively charged metallic knob. So, assume that you have a long chimney. In this, we have metal plates. These metal plates are connected to the current. If smoke is passed through this, since smoke is a negatively charged colloid, what happens is the smoke particles, I'm giving a different color, the smoke particles gets accumulated here. Carbon particle gets accumulated here. Now, when all the carbon particle gets accumulated here, the smoke is free from carbon. Therefore, it will not cause air pollution. Air pollution can be prevented by using a smoke precipitator. The smoke precipitator is otherwise called as Cottrell precipitator. It's called as Cottrell precipitator. Now, the next important application is formation of delta region, coagulation. Now, we know that during rain, floods, or natural disasters, river water, any river for that matter, they end up in joining the sea. During this natural disasters, what happens is this river water will carry a lot of mud particles, sand particle, and reach the sea. So river water consists of negatively charged clay particles or of colloidal dimension. When the river falls into the sea, the clay particles are collided by the positive Na+, potassium ion, magnesium 2 ions. So these all are the ions present in seawater. These all are the active ions. In river water, these active ions are not there. But this river water, which carries the mud particle, clay particle, all go into the sea. And in the sea, these active ions are present. These active ions, which present, they coagulate these negatively charged clay particles. And it forms a new land called as delta. Delta. So Sundarban, it's in Calcutta, which is a delta region. It's called as Sundarban. Next, clot formation. Blood consists of negatively charged colloid. This colloidal nature of blood explains why bleeding stops by applying ferric chloride solution to the wound. So if you apply ferric chloride, the bleeding stops because the ferric chloride solution causes coagulation of blood to form a clot which stops further bleeding. So colloids can be applied to form clots. Next, colloidal medicine. These three terminologies you should remember. Argyrol, protagirol, or colloidal solutions of silver. They are used as eye lotions. Colloidal sulfur is used as disinfectant. Colloidal gold, calcium, and iron are used as tonics. So colloidal particles are also used in medicine. So argyrol, protagirol, or colloid of silver, which is used in eye lotions. Colloidal sulfur is used as a disinfectant. Colloidal gold, calcium, and iron are used in tonics. So calcium tonics, iron tonics, all contains iron, calcium, and colloidal size. In Ayurveda, they use gold basma, wherein gold is a source of energy in the colloidal state. Coating of photographic plates. These are thin glass plates coated with a gelatin containing a fine suspension of silver bromide. The particles of silver bromide are colloidal in nature. So colloids are used also in photographic plates. Now this ends the topic surface chemistry, which we learned adsorption concept we learned catalysis, as well as we learned more of colloids. Now we'll have to learn with some of the questions based on the colloids. If we learn some of the questions based on colloids, the chapter colloids will be, surface chemistry will be done, and then we can go into a next new chapter later. A few of the questions we will try to solve. We have a few more minutes. We'll solve some of the questions. In the colloidal state, the particle size ranges from, it is a direct question, so the particle size should be between 1 nanometer to 100 nanometers. Please remember, they can give in centimeters, they can give in millimeters. Also, you should know 1 nanometer is how many millimeter, all that. So here for this question, the answer is option B. The main difference between crystalloid and colloid is, the main difference between crystalloid, the particle size is less than 1 nanometer. Colloidal size, the particle is between 1 nanometer to 100 nanometer. So that's the difference. Based on the size, we can classify particles as crystalloid and colloids. The third question, the next question. The phase in which colloidal particles are dispersed is known as inner phase, solvent medium, dispersed medium, dispersion medium. So the answer, the phase in which the colloidal particles are dispersed is known as dispersion medium. It's called as dispersion medium. It is not dispersed medium, it is called as dispersion medium, more precisely. But we learned as dispersed phase and dispersed medium. It's more precise, it is dispersion medium. The next question. Which one of the following forms Michel's in aqueous solution above certain concentration? Which of the following forms Michel's? Soaps form Michel's in aqueous solution above certain concentration. Urea, duodecyl trimethyl ammonium chloride, pyridinium chloride, glucose. So sodium or a salt will be salt of fatty acids or salt of a big molecule, big carboxylic acid will be called as a soap. Now, detergent, otherwise soap and detergent. Duodecyl trimethyl ammonium chloride forms a soap Michel, sorry, not Michel. The next one. Which of the following forms cationic Michel's above certain concentration? Sodium ethyl sulfate, sodium acetate, urea, cetyl methyl, trimethyl ammonium bromide. So which of the following forms cationic Michel's above certain concentration. Cation, bromide is negative and ammonium is positive. Therefore, it will be option D. Option D. The fourth question, did I make any mistake in the fourth question? No, it's correctly done. The next one. At critical Michel concentration, the surfactant molecules decomposes, dissociates, associates, becomes completely soluble. So at critical Michel concentration, the hydrophobic groups will align in one direction. So therefore, the process is called as association. It associates. Therefore, it grows into colloidal size. The seventh question. The method usually employed for precipitation of colloidal solution is the method usually used for precipitation of colloidal solution is dialysis, addition of electrolytes. It's addition of electrolytes. On addition of electrolytes, the colloidal particles will be neutralized and precipitation of colloidal solution will occur. Therefore, addition of electrolytes is important. So on addition of electrolytes to any colloid, what happens? The charge on the colloid particles will be neutralized and coagulation will take place, or precipitation will take place. The next question. The ability of anion to bring about coagulation of a given colloid depends upon its charge, the size of the charge alone, the magnitude of its charge, both magnitude and size. So it is both magnitude and size. It's according to Hardy's and Schultz rule. Coagulation is directly proportional to charge of the ion. Charge of the ion. The next question. During dialysis, only solvent molecules can diffuse. Solvent molecules, ions, colloidal particle can diffuse. All kinds of particle can diffuse through the semipermeable membrane. Solvent molecules and ions can diffuse. It is solvent molecules and ions can diffuse. Answer is option D. The next question. If a beam of light is passed through true solution, then it is visible, scattered, not visible, none of the above. It is not visible. See, when beam of light is passed through a true solution is called as crystalloids. Now, in case of crystalloids, no scattering of light takes place. So therefore, the path in which light travels is not visible. Hence, the answer for this question is option C. We will learn the next set of questions possibly in the next classes and continue with a new chapter. Ma'am, I'll stop the class, ma'am.
Okay, sir. Thank you, sir.
And